All right, this lesson is on graphing logarithmic functions. We're going to discuss two different strategies to do this. The first strategy is going to be using inverses, so we have to make that connection first. So this first slide asks us to look at an exponential function and a logarithmic function. Both of these are considered parent functions of both types. So we'll type in f of x. This is a growth function, right? It's the parent function, so we're looking for a horizontal asymptote at 0, and it's growing, right? My y-intercept should be 1. All right, you hit submit, and it's going to graph it for you. All right, now we're looking at log functions for the first time. Okay, so what is this going to look like? This is a parent function with a base of 2. Remember, the base could be different. Cannot be negative, can't be 0, can't be 1. The base could be any positive number other than 1. We're going to do base of 2. All right, hit submit. All right, so let's just look at some characteristics here for a second. Right, here's the red one is the exponential. We know it has a horizontal asymptote. Okay, and the y-intercept is 1 for the parent function. Right here, for the logarithmic function, our x-intercept is 1, so the y-intercept was 1 on the exponential, and now that becomes the x-intercept. Like x and y switched. And here, instead of having a horizontal asymptote at the line y equals 0, it has a vertical asymptote at x equals 0. Meaning that I cannot, my domain is restricted now. My domain cannot be any negative number or any number 0 or less, okay, less than or equal to 0, right? Because it can't be 0 either, right? And that should make sense on our understanding of basic logs, right? We know that what's in the parentheses here can never be 0 or negative, right? Because anything raised to a power, right, is not going to be negative or 0. So that makes sense. It's going to restrict our domain, whereas with the exponential, the range was restricted. And that's going to hopefully help us answer our next question. Are these graphs inverses? Well, we just reviewed what inverses were, okay, during block 1 and on Monday. Okay, inverses mean the domain and range are switched. The x and y's are switching, right? And that kind of makes sense here. So I would say, yes, this is, okay, they are inverses because the domain and range have switched, right? So think about it, for exponential, the domain was all real numbers, right? And the range was everything greater than 0. Now look at the blue function. Now the domain is everything greater than 0, and the range is all real numbers. So the domain and range switch. So you would say yes, because the domain and range switched. Okay, the other way we know that it is because if you graph the line y equals x, right here, I'll just do it, this dotted line right here, you can see that the graph it's a reflection. Okay, so that's another way. You can say yes, because two graphs are reflected over the line y equals x. Which is the definition, we reviewed that definition of an inverse, is it's a reflection over the line y equals x. Okay. So we learned how to graph exponential functions a couple of weeks ago. So let's take a look at doing this. So we want to complete the table. Okay, so this is a growth function. So we want to put our h in the middle. All right, our h is 4. So 2 numbers bigger, 2 numbers smaller. Now we've realized after our practice that really for a growth function, right, these 2 numbers smaller are just going to approach the asymptote. Okay, so our asymptote is y equals -3. So if I draw that over here, and I know this is a growth function, okay, so I know it's going to hug the asymptote before it starts to come up. Okay, now I've got to shift that over 4 spots to the right, so that's not the perfect graph, but I know that anything less than h is going to be so close I don't really need it in my table of values. All right, so if I start at 4 and I plug in 4, what's f of 4 equal? F of 4 is going to be 2 to the 0 minus 3, which is 1 minus 3, which is negative 2. And then what's f of 5? Plug in 5. So we're going to get 2 to the first minus 3, which is negative 1. And we'll plug in f of 6. We'll plug in 6. So f of 6 is going to be 2 squared minus 3, which is positive 1. And again, if we did do this, right, we plug in 3, right, we'd get 2 to the negative first, which is 1/2 minus 3, so that'd be negative 2.5. If I plugged in 2, it'd be 2 to the negative second, so 1/4 minus 3, so negative 2.75. And so those are unnecessary points. Okay, we want to know at 4 is negative 2, at 5 it's negative 1, and at 6 it's 1. Okay, so it's going to hug the asymptote, and then it's going to start to grow. All right. All right, we would know that the domain is all real numbers, and the range is everything greater than negative 3. All right, so we learned how to do that. All right, and then so we know how to graph exponentials. All right. Now, yesterday in class, okay, we talked about finding the inverse of exponential functions. So let's do that right now. So this is the same function that we just graphed. Okay, so if I said find the inverse, right? So we're going to replace f of x with y. And then we want to switch x and y because that's the definition of an inverse, the domain and range switch. So x equals 2 to the y minus 4 minus 3. Now we need to solve for y. All right, and that'll be our new function. So we're going to add 3 to both sides. So we're going to get x plus 3 equals 2 to the y minus 4. All right, and now we're going to rewrite using logs. Okay, so log base 2, or we'll go, I guess we'll go y minus 4 equals log base 2 of x plus 3. Now it's real important that we put the x plus 3 in parentheses. All right, because that's what the whole exponent's got to be. And now we just add 4 over to get the y by itself. So now we have log base 2 of x plus 3 plus 4. And this is the inverse, so we would rewrite it f with the negative 1. So the inverse of f of x equals log base 2 of x minus 3 plus 4. Okay, and as always, right, when we're talking about a, h, and k, the a would be in front, so the a is 1. The h is always attached to the x part here, so h is 3, and k is 4. All right, so this logarithmic function is the inverse of this exponential function. All right, and so we learned how to do that yesterday. So if I asked you guys, how can we graph this logarithmic function? So this is the one we just found, log base 2 of x plus 3, okay, plus 4. So it's the same exact, I don't know why I dropped the plus sign there. Same exact function that we just had. Okay, so let me go over that. I had a wrong sign there. Had it right there, but then I dropped For some reason I dropped the plus sign. Sloppy handwriting probably. Okay, log base 2 of x plus 3 plus 4. Okay, so if I ask you to graph that same problem, what ideas do you guys have? What can I do to graph this? All right, well, what do we know? We know it's the inverse of this function. So could we reflect it over the line y equals x and then graph it? Would that be a valid way? Would be. Okay, could we take this table of values right here and just flip it? So this column, my f of x column, my y column, my outputs here, my ranges, put those in the x column. Those become my range or my domain, right? And I take my domain here, the x's, put them in the y column, and those become my range. So I'm literally switching the domain and range. So I want to take this table of values and flip it, and that could work. All right. And so those are some strategies that we could use. Okay. All right. We can take the exponential graph, which is the inverse, and reflect it over the line y equals x, right? Or we take table of values from the exponential and flip the x and y's, domain and range. All right, so here's our exponential. Okay, we have the table. All right, so I kind of dropped the decimal ones; those weren't very helpful. Okay, and so now we are going to take this column over here, -2, -1, 1, and 5. Okay, and then take the x's, and those become my y's. 4, 5, 6, 7. So, right, if I can graph an exponential, if I can find the inverse of a logarithmic function, right, then I could write the exponential, I could graph that exponential, then I could just flip it. So if I could do the inverse of a log and I could graph an exponential, I can graph a log. All right, so if I graph these points, okay, I get -2, 4, -1, 5, 1, 6, and 5, 7. Okay, now I took away those decimals, but again, it will never be, it cannot go past this -3. Right, because no matter what I did on my table of values for this, my y values, remember my range is restricted. Okay, it's always greater than 3. So now my new domain, because it's the inverse, my new domain has to be everything greater than -3 for my x's. So what's going to happen here is these are just going to continue to get closer and go down towards -infinity. So my left end behavior, which is not really my left end behavior anymore, it's my end behavior as it approaches -3 from the right, is -infinity. And my right end behavior is positive infinity. All right, so there's my graph. All right, I just flipped the domain and range, the x's and y's, from my exponential. These two are inverses. F of x and g of x are inverse functions. We did that earlier. And we already made the table of values for f of x earlier. So we just flip it. Okay. Next question is, what do you notice about the horizontal asymptote of the exponential? What do you wonder about the horizontal asymptote of the exponential? So what do you notice and wonder? Right, so here's the horizontal asymptote. What did you notice about it? Okay, did you notice that it was k, right? We noticed that, all right? And then it was -3, and then you look over here, it becomes the vertical asymptote. Okay, -3. So the horizontal asymptote for an exponential becomes the vertical asymptote for a logarithmic. I wonder if that's always true. You look at the graph, okay, again, here it was k, here that -3 is h. So -3 was k, and it became h, right? And then h now is my vertical asymptote. Is that always true? So I'm noticing those things, and I'm wondering if that's always true. Okay. All right, we got a couple questions here for you. Okay, so on the left side of the screen it says, when looking at an exponential function, so here's the generic form, y equals a times b to the x minus h plus k, the horizontal asymptote is always the line y equals k. All right, when looking at a logarithmic function, okay, y equals a times log base b of x minus h plus k, the vertical asymptote is always the line, okay, and so based on the last one, right, it was h. Okay, so that's always going to be true. Okay, so it's x equals now because it's vertical. It's not y equals. It's a vertical asymptote, so it's x equals. So whatever h is, I'm always going to have a vertical asymptote at x equals h. Okay, a couple other true things. Okay, when looking at an exponential function, okay, a times b to the x minus h plus k, we know that b is always positive but cannot equal 1. Right? So when we're looking at a logarithmic function, that is also true. Is that base? Is that base? This base in a logarithmic function, okay, cannot be negative. All right, it's always greater than 0, and it's not 1. All right, so and then another statement here, when looking at the exponential function, okay, when a is positive, the range is always from the horizontal asymptote k to infinity. It's always above the horizontal asymptote. Now, if a was negative, it's been reflected, okay, but we're not going to be worried about that in this case. When looking at the logarithmic function here, the domain is always h to infinity. Okay, so just think about it. When we did the inverse, the k became the h, the domain and range switch, right? So that should make sense. Okay, but if the domain is always, okay, everything greater than h, that's what this is saying, from h and up, the x, when I can plug in a number, I can't plug in a number smaller than h because that makes this negative. Okay, and so it means that if it's h to infinity, right, so I could plug in h plus 1, that's going to be a positive number, right? Anything bigger than h, right, is going to create a positive number in here. So that means that x minus h is always positive. Okay, always positive. So why? Okay, so explain your thinking here. All right, and it should make sense based on our understanding of a log, since a log is an exponent, right? B raised to a power is never going to equal a negative number, right? And what's in parentheses is the answer. So there's no way, right, that we can have a negative number. You cannot do log base b of a negative. Not do log base b. Cannot do. Right? So we know that. So we know that x minus h must always be positive. All right. Can't even be 0. Right. So we know that. All right. Example. Okay. So if I ask you to graph log base 1/2 of x minus 2 plus 1. Okay. So step 1 is we want to find the inverse of this. So let's do that right here. So we're going to switch x and y. So x equals log base 1/2 of y minus 2 plus 1. So I'm going to subtract 1. X minus 1 equals log base 0.5 of y minus 2. Now I could rewrite it. Okay, so 0.5, I'm just going to switch that to a fraction. 1/2, right? The log is the exponent, so this x minus 1 is the exponent, equals y minus 2. And I'll just add 2 to both sides. Okay, and I'll go ahead and write it as the inverse of f of x equals 1/2 to 2 to the x minus 1, that all parentheses here, plus 2. Okay, so there's my inverse. Inverse of f of x is 1/2 raised to the x minus 1 power plus 2. All right, so now I want to make a table of values of this function. Okay, so I'm going to put h in the middle, which is 1. Do bigger, do smaller. And again, this is a decay function now. So really I just need to focus on h and the one smaller than it. So if I plug in 1, you get 1/2 raised to the 0, which is 1. 1 plus 2 is 3. If I plug in 0, I get 1/2 to the negative 1. So flip it, that's a revert, take the reciprocal, so that's 2. 2 plus 2 is 4. Okay, I plug in negative 1, I get negative 2, so that's 2 squared, which is 4. 4 plus 2 is 6. Okay, we can plug these in as well, but we know it's just going to be close to 2, right? So if I plug in 2, I get 1/2 to the first, which is 1/2. 1/2 plus 2 is 2.5. And you plug in 3, you get 1/2 to the second, which is 1/4. 1/4 plus 2 is 2.25. So these numbers are just going to get closer and closer to 2. Okay, so we flip the table. So my y's, okay, become my x's, and my x's become my y's. Now I like to always go in order from least to greatest, so I'm going to type in 3, 4, 5 right here, and then 3 was with 1, okay, 4 was with 0, and sorry, that should have been a 6. I don't know why I said 5. And 6 goes with negative 1. Again, I kind of just ignore these two. I don't need the decimals, okay? And I just flip, but I put them back in order because this was decay, so it was decreasing. So I went smallest, biggest, 3, 4, 6, okay? And then those match with 1, 0, negative 1. All right, so I have my new table. All right, and now I should be able to graph this. Okay, so if I plot those points, I should be able to graph, right? So 3, 1. Okay, so let's first draw my vertical asymptote, which is at 2. X equals 2. Okay, 3, 1. 4, 0. And then 6, negative 1. So you can see now, I compare them to the other log we looked at, right, where the right-hand behavior is going to positive infinity. Now the right-hand behavior is going towards negative infinity on this one. That's because the base was in between 0 and 1. All right, so again, let's talk domain and range here. So what's the domain of this function? Well, it's everything bigger than 2, the vertical asymptote. So we'll just go 2 to infinity. And again, it never equals 2, so we're good there. And then the range is going to be all real numbers. All right, and again, that's because it's going up forever. As it gets close to the asymptote, it's going down forever for the right end behavior. Okay, so let's complete the statements about the end behavior. So as x approaches 2, okay, and normally we say from the right. Okay, so as x approaches 2 from the right, it's going up towards infinity. Okay, so we'll just type in infinity right here. And then as x approaches infinity, it's going down towards negative infinity. So again, if I was just writing here, this would be infinity. And this would be negative infinity. Notice I don't go as x approaches negative infinity because x does not approach negative infinity. My domain, okay, furthest left it could go is 2. And it never actually reaches 2. It just approaches it, goes up towards infinity. Okay. Okay. Graph f of x. Okay, do your work on this slide and then graph on the next one. Okay, so you'll see there's a graph for you to do. So we got to do our work. All right, so what's our work? Our work is to find the inverse. Okay, so let's do that. Let's switch x and y. And if you know the pattern of how to do this quicker, you can. Okay, so y plus 1 minus 2. Okay, so I'm going to add 2 first. So I get x plus 2 equals log base 3 of y plus 1. Now I can rewrite it. 3 to the x plus 2 equals y plus 1. And last step is subtract 1. So I'm going to get the inverse of f of x equals 3 to the x plus 2 minus 1. All right, and the shortcut is the h and k's switch spots, right? The k was -2, now h is -2 in the exponential. The h was -1, and now the k is -1. All right, so the base stays the same. All right, so now that we have that, we can make our table values. This is a growth function. So I'm not gonna worry about all the fraction ones. So my h is -2, and then I'm gonna do the next number is bigger than it. Okay, you could do more than 2 if you want to, because I'm not gonna worry about the smaller ones. So if I plug in -2, I get 3 to the 0, which is 1. 1 minus 1 is 0. Plug in -1, I get 3 to the first. 3 minus 1 is 2. Plug in 0, 3 squared is 9. 9 minus 1 is 8. Plug in 1, I get 3 cubed, which is 27. 27 minus 1 is 26. Okay, so again, this point obviously is going to be off my graph. All right, but that's my table of values. Okay, so now if I flip those tables, right, flip it, right, what's my new one become? Okay, my new one, back for the original f of x, okay, I'm going to get 0, 2, 8, and that's -2, -1, 0. That's what I'm going to be graphing. All right, so we're going to start with our vertical asymptote, which is -1. So we'll draw that, and then we have the 3 points from the table of values we just made. So let's plot those 3 points: 0, -2, 2, -1, and 8, 0. Okay. And then 2, -1, and 8, 0. So you can see our graph. Looks like this. Now we want to state the domain and range. So scroll down, the box is right here. So our domain, right, it's from -1 to infinity. And then our range, all real numbers. All right, so now that we know how to graph using inverse functions, can we graph without using them? So is there a way to graph, okay, a log function, a times log base b of x minus h plus k without finding its inverse? Okay, and the answer is yes. Okay, since we know that a logarithm is just an exponent, we can pick values of x that make x minus h equal to a power of b. Okay, so to create the table of values. So what I mean by that is we want to be able to mentally be able to calculate what log base b right can be. All right, and so if we want that to be 0, we would go b to the 0 equals x minus h. So what's x have to be? Okay, x would have to be b to the 0 plus h. So I can pick my x based off of this, right? So if we'll do an example, but I'll come over here. If I go log base 3 of x minus, or let's go x, yeah, minus 2. Okay, so that means h is 2, right? What's the first x value that I want to choose? Okay, it would be 3 to the 0 plus 2, which is just 3. Watch what happens when I plug 3 in. 3 minus 2 is 1, right? So I'm asking you, what is log base 3 of 1? Which we know, 3 to the what power is 1? That's 0. Okay? If I want my y to be 1, right? If I want this to equal 1 over here, it's going to be very similar. B to the first, so it's a power of b, right? Equals x minus h at h. B to the first plus b to the first plus h equals x. That's what I'm going to choose next, right? So 3 to the first plus 2, that's 5. I'm going to plug in 5. And guess what happens when I plug in 5? It's going to equal 1. 5 minus 2 is 3, right? So now it's log base 3 of 3, which we know is just 1. 3 to the what power is 3? That's 1. All right, if I do this for 2, all right, now b 3 squared is 9. 9 plus 2 is 11. If I plug in the 11, 11 minus 2 is 9. 3 to the what power is 9? 3 squared is 9. And so there's my table of values. I just need to be able to create those x's, and it's all based on what my base is, okay, and what I want it to equal. We always think if we could do powers of b, it's going to be easy to figure out. Okay, another thing to consider is that x minus h is always positive. Okay, so we will always start with the value of x that is 1 larger than h. So notice, h is 2, we started with 3, all right, because it's always going to give you 1, and then we'll always give you 0. Now, if there's a k, you have to add a k to that. We'll talk about that in the next slide. Okay, this next slide is for your notes. Okay, so here's the pattern. Okay, this is what you're always going to do. Okay, so when b is greater than 1 for a log function, okay, this is how you'll make your table. So your x's, you'll just start with b to the 0 plus h, and b to the first plus h, right? B squared plus h. B, how many you want to do? I mean, normally you're going to get too big when you get to b cubed, right? That's b, that's only 8. But all right, you probably never want to do more than 0 through 3. All right, and then your y values will always be, okay, a times 0 plus k, a times 1 plus k, a times 2 plus k. So the k is always there, all right, and so it's just going up by a every time. Okay, your output column will always start at k and then go up by a. All right, because a times 0 is always just 0, so this first one's always just k. And then 1 times a is a, so it went up by a. Now there's two a's instead of one a. Now there's three a's, right? Hopefully that makes sense. Okay, and then right here, for if b is a fraction between 0 and 1, okay, so now we've got to be able to flip that fraction. So we want to use negative exponents, okay? So we'll start with b to the 0, and then we're going to go b to the negative first plus a, b to the negative second plus a, and so forth. And then now our y values are going to start at k and go down by a. All right, so that we noticed that on that example that we did where b was 1/2, right? The right end behavior is going down towards negative infinity. All right, so this is good for your notes. So we could kind of bypass doing all the inverse stuff every single time and just pick these values for x, and then the y's will be easy. It's just whatever k is, right? And then add a every time or subtract a every time. You got to know how to get your x's. Again, how am I picking my x's, right? I'm thinking back, okay, to this problem, right? What is going to make it easy for me to figure out what makes x minus h a power of b? All right. So, right, 3, right? What makes it 9? So I could get 2. All right. So we want to graph this one. All right. And so we'll start with my x's. So b in this case is 3. Okay. So 3 to the 0 is 1. Right. And then h is 1. So we're going to start with 2. Okay. And then b to the first. So 3 plus 1 is 4. And then 3 squared, okay, is 9. 9 plus 1 is 10. Now this one's going to get a little bit big here. 3 cubed is 27. 27 plus 1 is 28. Okay. You could also, right, if we're in Desmos, so you could technically type that in, right? 3 to the 0 plus h, and h is 1 in this case, and it's going to calculate that for you. 3 to the first, 3 to the first plus 1. 3 to the second plus 1. 3 to the third plus 1, right? And so same numbers that I got when I did it verbally in my head. Now we know this is always going to be k. This is going to be 3. Then it's going to go up by a. So it's going to go up by 2. So 5, 7, 9. And we could just double check real fast, right? If I plug in 10, 10 minus 1 is 9. So log base 3 of 9 is 2. 2 times 2 is 4. 4 plus 3 is 7. So, right, it does work. Right, and then we graph this. So I'm going to draw my vertical asymptote at 1. My domain is all real numbers greater than 1. And I just plot these points. Okay, 2, 3, 4, 5, and 10, 7. There we go. Another example. So now we have a number in between 0 and 1 here. So log base 1/4 of x plus 2 minus 1. All right, so here's our base is 1/4. All right, and so again, if we go 0.25 raised to the 0, and this time h is -2, so minus 2. Right, 0.25 raised to the first, minus 2. Oh, I made a mistake. What did I do wrong? I don't want that decimal. What? So what am I doing wrong here? Oh, it's in between 0 and 1. So now I need to make my exponent, right, a negative because I want to flip that. That looks better. Okay, what about, so 0.25 raised to the negative second minus 2, and 0.25 raised to the negative third minus 2. These are the numbers that I'm plugging in. Obviously, that's going to be a little bit too big here, but I know, again, we know it's just going to start at k, which is -1. And this time it's going to be going down by 1. So 0, 1, 2. Okay. So my vertical asymptote is at -2. And so I have -1, -1, and I have 2, 0. And that's pretty much all that's going to fit on my graph. Okay, 14, 1 is off the graph over here. All right, so as I draw this graph, and make sure you don't go above 1 when you hit the edge there. So my graph's going to look something like that. All right, and so you should try this one. So let's see if we can do this one pretty fast. So what x's am I going to pick, right? So it's all going to be one more than h. H is -6 here, so this is -5. All right, and then I'm going to do 4 to the first, so 4 minus 6 is -2, and 16 minus 6 is 10, and now we're off. 4 cubed is 64. 64 minus 6 is 58. Here it's going to start at k, which is -2, and it's going to go up by 1 every time because a is 1. 3 of these will fit on my graph, so I'll draw my vertical asymptote at -6, x equals -6, -5, -2, -2, -1, and 10, 0. Oops, that was bad. All right, and that's how you guys graph logarithmic functions. So there's 2 strategies. Okay, find the inverse of it, make the table, switch the table, graph it, or know how to find the correct x values. Okay, by understanding that logs are exponents, and if I could get the right base to be the right power, okay, I could easily figure out what values to plug into h that are easy to calculate. All right, so there you go.